Okay, one of the questions I had was, wait, what's a Bayesian classifier? It's in the notes, but I don't remember it in class. There was half of a slide on it in other classifiers. The only thing you really need to know about it for the test is that instead of using a threshold to say everything above 0.6 is going to be true, everything below it is false, the way a Bayesian classifier works is it's going to say, okay, there's a 0.6 that it's true, there's a 0.4 that it's false, 0.6 is bigger than 0.4, therefore it's true. So it can give you positive class prediction even when you have a very small number, or it can give you a negative even when you have a very big number, simply because it's caring about the differences in size. I'm now going to talk a little bit more about what Bayes' theorem is for interested parties, because I think Bayes' theorem is really important. Basic idea up here, we've got Bayes' theorem. It's the probability of A given that B happened is equal to the probability of B given that A has happened times the probability of A times over the probability of B. What does this all mean? It means that you need to take into account how likely something is to happen, as well as how likely a test is to say something happens. It's important when you need a difference between them. Even if you have a very accurate test, you can wind up with, oh, our test is 99% accurate, but when it's right, it still probably means no, they're not in the bad case. Some of the textbook examples that are frequently given are things like, let's drug test welfare recipients. Well, if you look at what proportion of welfare recipients use drugs and versus how many don't, it means that even among those who do test positive, they're more likely than not to actually not be drug users. That's why they have to do a second follow-up confirmatory test. Lots of medical things actually wind up in a similar boat, but that's the basic idea we've got going on here. So what I've got here for my data, I've got 10 employees. I know whether they actually use drugs, because the supervised algorithms we have are true, and I have whether they tested positive for taking drugs. I will now figure out what P of A and P of B are for each of these, and I will plug it into the formula up here, and I will write it down for all of my different possibilities. So the possibility are, what's the probability they are a drug user given the test said they are? What is the probability that they are not a drug user given the test said they were? What is the probability that they are a drug user given the test said no? And what is the probability they aren't given the test said no? So those are the things. We're just going to go and get all these probabilities by counting them out. So our first case, we have A and B are both true. So the test says they're actually a drug user A. The test says they're a drug user B. P of A, P of B, P of B given A. So P of A, what's the probability that someone is a drug user? 1, 2, 3. So if 1, 2 out of our 10. What is the probability that someone is going to test positive for doing drugs? 1, 2, 3, 4. Also out of 10. We still have 10 employees. P of B given A is, given that we already know they're a drug user, how many of them will wind up testing positive? So of our 2 people that really are drug users, here and here, how often does it say yes? So drug user true. Make sure that's lined up correctly. Cool. So drug user 2, drug prediction true. Drug user 2, prediction 2, 2 out of 2. Plug it into Bayes' theorem. What do we get? We get 2 out of 2 times 2 out of 10 over 4 out of 10 is equal to 0.2 over 0.4 is equal to 0.5. So I'm going to go right down over here, 0.5. Now I'm going to track down that eraser. And erase all of this, and repeat it for the next one on the list. So, given that they have, let's see, what am I doing this in? Given that they tested positive, what are the odds that they are not using drugs? So, what is our P of A? This is how many times that their actual drug use is false. That's going to be 1, 2, 3, 4, 5, 6, 7, 8. What is our probability that they are going to test true? 1, 2, 3, 4 out of 10. Of cases where of cases where they were actually drug users, how often did the test say they weren't? So, we have how many cases where it's actually false? 8. For those 8 cases of not using drugs, how often did the test say they would? No, no, no. There's one. Wait a minute. God fucking damn it. So I'm going to fix this to keep the numbers right. So now our T's still line up. Sorry, this is just, anyway. So of cases where they actually did not take drugs, how often did the test say yes? Nope, nope, nope. Oh, there's a case where they didn't take drugs, but the test said they would. There's another one. So we've got 2. So of the 8 times that of the 8 times that someone was not actually a drug user, the test said they were twice. So, put this back into the theorem. We have 2 out of 8 times 8 out of 10 divided by 4 out of 10 is equal to 0.2 over 0.4 is equal to 0.5. So, what's our classifier going to do here? If it encounters someone that the test says did take drugs, there is a 50-50 chance that they're actually a drug user, because these are equal. It'll probably just tell us, hey, equally likely. Now let's try it on the other side. So now we are going to look at if they tested negative, what are the chances they're actually users? So, A is true. A is true 2 out of 10. B is true. B is false 1, 2, 3, 4, 5, 6 out of 10. Of the 2 times that A is true, how often is B true? How often is B false? 0. Yes. Because when it is actually true, yeah, true. Cool. 0 out of 2. So this gives us 0 out of 2 times 2 out of 10 over 6 out of 10 is equal to 0. So the probability that they are going to be a drug user, given the test said they aren't, is nada. And very last one, F and F. So How many times is drug use false? 8. How many times is test positive false? 6. Of the times that it is actually false, how often does the test say it's going to be false? 1, 2, 3, 4, 5, 6. So that is going to give us 6 out of 8 times, excuse me, time here, 8 out of 10 over 6 out of 10 is equal to 0.6 over 0.6 is equal to 1. So what does this give us? Whenever the test says false, we're going to give it a label of no, they're not a drug user. Right. Whenever the test says false, we're going to give it a label of false, because this 1 is bigger than the 0. Whenever the label is true, we're not sure what to do. There's even odds. The interesting and useful things that come out of this are you could predict multiple different classes with it. So instead of true false, I could predict pot, cocaine, nothing. 3 classes, it's not really different here, right? The other thing is that you can multiply these together since they're all probabilities. So if I have multiple features, so I have a urine test and a blood test, I can run and calculate this for urine, then run and calculate it for blood, multiply those together, and then I wind up with the same kind of predictions. And that's the best I can do on Bayes' theorem when I'm this tired.